All right. Hello, welcome everyone. My name is John Hay from University of Nebraska. We're going to have a fun presentation today on ethanol and fuel characteristics and some fuel, kind of basic fuel 101. Our speaker today, Steve Vandergreen from ICM, is full of information from work he's done, work that ICM has done, and review of studies from a whole number of different groups. And so just he and I have had some really good conversations just leading up to this, and I feel like I've learned a lot. I'll let you get started, Steve.
Well, thank you, John. Again, my name is Steve Vandergreen. I work for ICM Inc. here in Colwich, Kansas, just outside of Wichita. My primary hat is the Urban Air Initiative, which we started a couple years ago. But this is really kind of summarizing a lot of the work ICM has been involved in and what we've learned from octane to fuels. We've converted diesel engines several years ago to run on hydrous ethanol to being at the ASTM meetings over the past few years. So I pulled together some slides here today that hopefully will not be too much at one time, but I am going to touch on just general ethanol, gasoline, kind of 101, and then a little bit of the octane story that the auto industry has been championing over the past few years of more of the mid-level blends as well. We're looking at mid-level blends up to E85 as far as marketplace strategy. Just to introduce, again, ICM has been in business for 20 years, and our goal is sustainable agriculture. And so a lot of the things we've done over the past few years is some of our bolt-on technology for thermal oxidizers, oil separation, fine grind. Today we're looking at kind of our cellulosic 1.5 and 2.0. Our designs in the ethanol business, we're about 102 plants are ICM design, and we've done ethanol plants even in Mozambique and Argentina. If anybody is interested, our R&D plant in St. Joe, Missouri is a food processing plant as well as an ethanol plant, and that's where a lot of our R&D is. So that is probably an area you could take a tour if interested. So now I just want to jump into a little bit of the ethanol history, kind of the ethanol 101. Some people, again, don't always know this right offhand, but there's been a long history of ethanol. Even in the first internal combustion engine, it was using ethanol back in 1826. In the later 1800s, the Agriculture Department in 1872 reported 90 million gallons of ethanol being used. A lot of that was going actually into the kerosene at low levels to help reduce soot from the lanterns. And then in 1908, Henry Ford's first Model Ts were actually flex fuel vehicles, and the consumer had to know if he was changing his fuel blends to actually make an adjustment right there on the carburetor. The octane story actually always is dated back even to 1922. Thomas Megley with GM had patented or approved patent for E50. And so that is interesting, but unfortunately 3 years later, his patent for tetraethyl lead was approved, and that's kind of the whole story of the tetraethyl lead and alcohol, dates back many, many years, even to that people don't recognize. As we look at kind of again at ethanol, since we're talking about a simple common component here, when we add ethanol to gasoline, there are a lot of things that are very predictable. We know what the octane will do, the vapor pressure, the volatility. Ethanol has a cooling effect, which is a huge part of octane, and we'll talk about that in a little bit. It's really the latent heat of vaporization. It's how much heat is absorbed to actually vaporize the fuel. So it's 4 times gasoline on a energy content, 3 times on a volume basis. Distillation is also very predictable, but it's very unique, and that's going to be the second part of the focus after we talk about octane here in a little bit. And then ethanol has a good carbon to hydrogen ratio, and that's part of the reason why even today FFE certification is usually around 7 to 8% less CO2 per mile than it is on pure gasoline. So even today there's some CO2 reductions just from the chemistry of ethanol versus gasoline, and it's low toxicity. A little bit more of the 101. A lot of times I think when you search the internet, you'll find varying levels of BTU values. It's very consistent, though, in the automotive studies. And again, we need to be using the low heating value. Often we can see on the internet people don't understand the difference between high and low heating values. But on general, gasoline is about 114,000 BTUs per gallon. It'll be a little higher in the summer and a little lower in the winter as the vapor pressure changes and they shift to lighter hydrocarbons. For gasoline, one of the main octane components is aromatics. They're all some form of benzene. So that variation of gasoline, I'll have a picture here in a minute to kind of outline that. But again, it takes more energy to create the aromatics, and they also have more carbon per unit of energy. So in a little bit, I'm going to show you from the gasoline and the automotive perspective, kind of this good, the bad, the ugly from an octane point of view. Ethanol, again, from E0 to E30 has a very, very high octane increase, and I think later you'll see how the octane of ethanol is actually not a linear response, and I think that's a huge part of what's driving some of the discussions around ethanol from an octane perspective. One of the first things I do need to explain, though, is the differences between splash blending and match blending. And this is very, very important as you start looking at what studies you're actually going to reference around the value of ethanol. I've actually got a stack of roughly 15 studies in an envelope, and one envelope all the studies are positive for ethanol, and the other one they're somewhat negative for ethanol. And the key difference is how did you prepare the test fuel? In splash blending, if we're talking about E0 to E10, when we simply add ethanol to current E10 today, we would start to reduce the vapor pressure, which is kind of that concern from E0 to E10. We would be allowing the increased octane to the consumer, and there's some neat performance papers out there when you look at testing from 87 consumer octane. We should also see, reductions in the regulated emissions, the particulate emissions, and if you're able to just simply add the ethanol, you're giving that octane can help offset any mileage difference in these lower levels of ethanol blends. The other concern is match blending, and a lot of these studies will sometimes match blend octane or match blend distillation, vapor pressure. And so you really have to understand what did the oil company do, because a lot of these fuels are provided by the oil companies when they do studies. What did they do to the base fuel that changed? And there's a significant concern going on today around match blending distillation, because very few people have looked into this. So you will hear me talk a little bit more about match versus splash blending in the slides to come. So again, what is gasoline made of? And why do we accept this monopoly that, is gasoline an additive or is it a component of fuel? This picture is from Oklahoma, but, you have to ask yourself, what is pure gasoline? When you start looking actually at the data and the market survey work, people probably don't realize just how much variation there is even in gasoline from one refinery to the next, even though any given region area may be the same. But in here, I've just got listed, just the multiple aromatic components that you could find, and some of the other additives that may not even be present in test fuels. So I kind of like to just mention, that there's been no beaches closed due to ethanol, and if we did have an ethanol spill, most of the critters would probably be on the happy side if we had an ethanol spill. It usually gets a few people to laugh, but again, going back to gasoline, I think it'd be interesting for people to realize you could actually buy 35% of your fuel at Lowe's or Home Depot in the solvent section. Mixed xylenes are all aromatics. They used to sell toluene until they kind of started to look at the health issues, which xylene may sound fine, but it's dimethylbenzene. So you can go to Home Depot and buy the xylenes or alcohol as a glass cleaner or actually a cook stove fuel. But that does somewhat represent 35% of our gasoline today. This the slide here is to kind of put gasoline in the perspective from the automotive engineers. Every SAE paper will usually list the saturates, the aromatics, and the olefins, along with a lot of the other fuel properties. To the auto engineer, the saturates are good, the aromatics need to be carefully watched, and the olefins tend to be, in a lot of test fuels, they may not even add olefins, but this is looking at consumer gasoline today, and the straight chain hydrocarbons are lower in octane, but then you actually get better in cetane. So, as you transition to the saturate long chains, that would be actually beneficial for diesel. Here is isooctane, which is actually the pure hydrocarbon for the octane testing, RON and MON being 100 octane. And I'll explain the RON and MON here in just a minute. The primary concern, though, is going back to these aromatics. They're all some form of benzene, and they're a key part to the pH and toxic emissions and then the particulates, which is becoming more of a concern in especially gasoline, but it's even part of diesel. Today we have diesel particulate filters. There are some in the auto industry that are concerned that in 5 to 6 years they may be even looking at regulations for particulate filters on gasoline vehicles. But here's benzene and butadiene as your two top carcinogens, and a lot of that has to do with the double bonds of these hydrocarbons. So that's, in general, a breakdown that you could find almost in every automotive study, though the refinery would look at it from multiple different streams. Now I've kind of covered a little bit of the gasoline 101. I'm going to be trying to do a quick overview on octane. I think that's a pretty hard thing to do in a half an hour, but to 45 minutes. But the first paper is actually, this first one was published in 2012. ICM and AVL actually initiated this work, and then John Deere and Ford Motor Companies joined on. This is probably the largest octane study ever conducted at this point that we know of. And it's really kind of the interesting story about ethanol and its octane. We've also done some other ones in 2013, and this is a link you could go to as John would send out the PowerPoint presentation. So what we probably need to explain first a little bit, and why I'm going to be using ethanol versus toluene is the highest octane component of gasoline versus ethanol. But there's also what we call the RON and MON of fuels. This may be confusing if anybody starts to research automotive papers or technical papers, is a lot of times the auto industry is focused on RON. Sorry about that. But the RON stands for Research Octane Number. That's ASTM D2699, and Motor Octane Number. The auto industry is primarily looking at RON because that is more of your light load, lower RPM operating conditions, and the motor octane number is more for racing, and it's actually aviation gasoline is sold on the MON number. But only here in the U.S. do we actually use this AKI value, and this is something you would see on every pump in the United States. It's actually required to be there. In Europe, you'll only find the RON number, or in Asia. So there's always that, if you travel, you're going to probably think, wow, that's much higher octane. They generally do have higher octane, but they use only the RON value. So in a little bit, I'll be coming back to the ethanol versus toluene and true octane performance. But again, in case I accidentally use RON, RON is typically higher than the AKI, and the MON is the low number. Our study on octane was trying to mimic ASTM standards. So we actually had 3 different fuel systems, and we had 7 fuels. All the ethanol blends were splash blended, and what we were doing was testing the knock limit of the fuel. But we used an upstream fuel injector prior to the temp sensor to offset ethanol's cooling effect. And we've learned some really, really neat things. Even engineers on the phone were saying we really didn't know this or understand this until this study that was done a few years ago. But as the auto industry moves more towards the direct injection, where they're actually injecting the fuel in the chamber, nowadays probably under a few different pulses to help reduce PM, you're able to get the full cooling effect of ethanol in the chamber, and that's part of the neat octane story of ethanol. To explain a little bit on efficiency and why direct injection and why turbocharging is that efficiency actually goes up in load. Along the bottom axis here is actually a measurement called INMEP, an indicated net mean effective pressure. This is how the auto industry measures the workload of each combustion event. So as they try to do more down speeding, more variable transmission speeding, multiple speeds in the transmission, what they're trying to do is raise the effective pressure of each combustion event. And in so doing, they're able then to look at raising the efficiency of the engine. So this is really the focus of the auto engineering, people is the value of turbocharging. The y-axis here is just the net thermal efficiency of combustion. I've charted out the gray here as you probably won't see any engine anytime soon actually get up and operate much over the measurement of 25. So that's really not in an area the auto industry is looking. And if you're looking up here, you're really getting into diesel territory. So this is a means of getting higher efficiency, but you also have to plan for it to take full advantage. So again, maybe a little challenging to fully describe this chart. More than happy to spend time afterwards or with somebody if they're interested in this more. But what again is you're seeing that same measurement across the bottom, but now we're seeing what we call CA50, which is what the crank angle did 50% of the fuel burn. And peak efficiency usually happens around 7 to 10 degrees after top dead center is where you're going to see your peak efficiency. So each one of these points represents the knock limit of the fuel. We retard our timing a little bit and then try to experiment all the way to significant retarding of timing. How does the fuel respond? And a lot of studies, don't explore this, but the auto engineers rely on this quite a bit because anytime you get on the freeway, drive high loads or high speed, you will spend some time where your ignition timing has to be retarded for the knock limit of the fuel. And what I'm just trying to point out here is that these points on the left actually line up with what's on the right. And right here again, as I mentioned earlier, isooctane is the 100 octane scale. If we actually measured E30 for octane for our fuel pumps, we would see less than 100. We'd probably see about 94 AKI. Yet in performance, this fuel performs better than 100 octane, especially in the area where you're going to be doing most of your driving. So that's very important to the auto industry for efficiency. So kind of summarizing a lot of this data, here on the left we're seeing simply adding ethanol to a consumer regular and premium bob. And so today in E10, we're probably around a 92, 93 RON value, which is about 87 AKI. And then up here with E30, we're actually sitting around 100 RON, which would be about a 94 AKI. I think what's interesting to point out here is the blending value. You're seeing a 14-point increase from E0 to E30, but you're only seeing the 7-point increase from E30 to E98. So ethanol has a unique increase of octane. There is another paper that we worked on with Ford that actually explains that, but that would be a challenge to explain on this presentation. But Ford is actually able to make this linear because by E30, over half the mole fraction is ethanol. And so from down to a mole fraction, they could actually plot that as a linear. But then E30 ended up being in the middle of the chart. So as we look at these lower level blends on the right, again, this is the measured octane from on the chart in the solid lines. But then Ford was able to actually add on the performance of the octane fuel. And so now you're bringing, instead of 100 RON E30, you're actually up around 108 RON performance. And again, this is for direct injection. It would be a little lower on these dash lines if we're looking at port fuel injection, kind of the older technology we have today. So going back to kind of understanding how ethanol has been treated from an octane perspective, a lot of the analysis, cost analysis, was looking at neat value. If you were testing 100% toluene versus 100% ethanol, toluene would actually have 112 AKI octane, where ethanol would only respond to about 100 AKI if you were going to test the fuels at 100%. Now, no one's going to run their car at 100% toluene. It would be awfully dark particulates coming out the tailpipe if you did so. So we're trying to understand what is the blending value. What does it do in that first 30%? And then if you just draw that out, we actually flip-flop the values here, where toluene's blending value is 104, and ethanol is running about 120 AKI. For every gallon you're making, you're increasing the octane of 3 or 4 gallons of E25 or E30. That is the octane value that the refineries have already been enjoying for E10. But again, the values here are substantially different, and there's nothing in the gasoline pool that can do this. But again, this isn't new. This is right out of Refinery Handbook from 1989, and it's based on E10 data. But if you're going to look at the neat octane values of benzene or toluene, toluene here is the highest octane component, listed at 112 for neat value, where ethanol is 100. But the refineries already knew that the octane blending value for E10 put ethanol above any other component from an octane side. So this is really one of the big drivers for getting E10 into the market as we know it today. So again, that may be a little bit, a lot of technical data. John, is there any questions up until this point that maybe I should address?
Yeah, not yet from them. I do have a question though, and maybe this will bring up some of their questions. But what's going on in the engine that causes ethanol blends to have lower PM, particulate matter? Why is that happening?
Well, in the additional attachments, which I wasn't going to review, them couple extra papers, the PM formation really starts with aromatics creating PAHs to UFPs. So you have to first create the cyclic structure. Ethanol, like a lot of the light ends of gasoline, it actually takes 19 reactions to have ethanol form just a benzene ring, a cyclic structure. Without creating the cyclic structure, you do not have the building blocks for creating particulate emissions. So that's really, when you're talking about a two-carbon, hydrocarbon that's already in some ways partially burnt, going down the pathway of CO2 and water, it becomes very difficult for ethanol to create soot. In the challenges we're dealing with at the EPA right now, the EPA is trying to say, well, ethanol raises particulate emissions because ethanol's cooling effect hinders the fuel's ability to fully vaporize. But again, all their data they're using to say ethanol raises particulate emissions are all based on match blending, and all the work we've done or the data we've collected says ethanol lowers particulate emissions when you simply add it to gasoline. But I think when you look at a lot of the vehicle studies, now this one was simply adding ethanol to EPA certification fuel, we have some pretty nice results for the mid-level blends. We do have some increase sometimes with the 85. We have ethanol percentage at the bottom. We have weighted tailpipe emissions here on the y-axis. This was an FFE. Great study to talk about fuel chemistry and engine calibration. So this is, kind of the value of simply adding ethanol we see. But again, the consumer fuels are a lot different in emission values. So don't want to go, I could give a whole hour and a half presentation, but this chart here, this ASTM test for distillation is the center of our entire argument of why EPA came to the wrong conclusion on ethanol. Ethanol does something uniquely different, but the study EPA did is they matched T50 and T90. So what they're doing in this study is they're raising the distillation temperature on the y-axis and then recording that temperature as the fuel distills. So here's your T10. At what temperature did 10% of the fuel distill? And here's what temperature did 50% and 90%. This is a huge whole subject in itself, but as you simply add ethanol, you do something uniquely different in that you kind of get this knee of distillation. Right here is E10, and here's E15. The only way you can drive up this T50 for E15 is to add higher distillate hydrocarbons up here. This knee of distillation is when ethanol actually comes completely out of your 100 milliliter sample. This is really the key of our argument. This testing is used for the vapor lock equation, drivability of the fuel, and yet nobody has really investigated how ethanol uniquely is different. And I could do a whole presentation on just this ASTM practice and some of the other studies that are out there. So as we look at, again, this study from 2006, which is the basis for the EPA study, you had 2 of 4 E10s prone to higher emissions by the addition of higher distillate hydrocarbons up here. Yet you had 4 of 5 E0s that all got the same emissions because they have a fairly lower distillation all the way up to about T80. So this is, again, not simply adding ethanol, but if you go to this study, which is public online at the Coordinated Research Council website, and you read the results, it says increasing ethanol raises benzene, increasing ethanol raises total hydrocarbons. But when you simply add ethanol, it also says raising T50 raises benzene, but if you simply add ethanol, ethanol lowers T50. So again, this is hugely important and probably worthy of its own discussion entirely. But the problem of this whole EPA study on 27 fuels is, on the track record, it's influenced Tier 3. It's in the MOVE's Motor Vehicle Emission Simulator model that was just released fall of last year. We've run that model for Chicago and Kansas City, and E15 doesn't look very good. So you have to, again, go back to, how the fuels are blended, and none of these were based on splash blending. Just two more slides here. This is actually out of the EPA report. When you keep aromatics equal at the same percentage, RVP, T50, and T90, all these emissions with increasing ethanol right here, all these emissions goes up. So they're trying to treat these 5 parameters as individual ones, yet ethanol affects every one of these. If I took E10 today and I removed the 10% ethanol, we would lose the dilution. Your aromatic content would go up, your vapor pressure would go down, T50 would go up, T90 would go up. So it's a little hard to explain. If I remove ethanol and I change these parameters, all these emissions goes up. The problem is, can you move it in the model enough to offset how the model works? And again, the model is not real world. Ethanol does not raise these emissions. The model says it does. And then just one comment on permeation. We're doing vehicle studies. Benzene and toluene are the most aggressive for some of the small engine issues, swelling of plastic, permeation. But also the non-aromatics are important here as well. So we have to address the test fuel they use for this kind of testing work. And here's just over 16 days, the permeation rates of adding individual components at 10% to an E0. So here's E10 is one of the lowest besides iso-octane, but you have toluene and pentane up here. There's a whole issue of match blending versus splash blending when it comes to permeation, because permeation is actually 60% of vehicle evaporative emissions. So in the model, we raise vehicle evaporative emissions, yet none of that is based on splash blending ethanol. There's actually more aromatics in the E10 than there are in the E0. This picture right here is off of Husqvarna. It's actually before and after soak testing in E0 after just 4 weeks, but we were pulling it out every day and letting it dry and then putting it back in. The problem isn't ethanol, and it's not gasoline either. It is the fact this line shouldn't be in service. They have a poor line, but unfortunately, it's things like this is where ethanol gets blamed. So just briefly, we have 3 websites. The Urban Air Initiative is bringing the awareness of aromatics and health concerns. We also have a website on Fix Our Fuel. And I had just mentioned to John earlier this week, but we have a website that will be coming out where we're trying to just give simple facts to the consumers, to the dealerships, and to small engines. And so we're hoping this would be a kind of a go-to place for a lot of the things we're talking about today. And with that, that's the end of the presentation.